Hello, hello. Let's see. Switch on the screen. Yes. How was you guys' day today?
It was okay. How was yours?
It was very restful because I'm not back in school yet. I'm still in break, so I've been like resting a lot at home, walking my dog more. So no stress yet. No stress yet. Are you guys stressed yet, or are you guys like chilling right now?
I'm stressed.
You're stressed?
Definitely.
And this is week one, right? For you guys? Week one?
Yeah.
Oh my gosh. So we could get started with one HCC stuff. Yesterday we did the carboxylic acid reactions. Now, like we didn't go over the Grignard reaction or the reducing agent, but we'll go over that after. I'm gonna keep going with the interconversion between the derivatives, like how to convert between the acyl halide, anhydride, carboxylic acid, ester, amide. So now let's talk about the most reactive derivative, the acyl halide. An acyl halide is going to have a halogen like chlorine or bromine attached to the carbonyl. So this is an acyl halide right here. Because this is the most reactive derivative, this acyl halide here does not require heat or any catalyst, like base catalyst or acid catalyst. Does not require heat or acid or base catalyst. Right? So, for example, let's convert this into an anhydride, one derivative lower than this acyl halide, right? If you see a neutral carboxylic acid, right, alone with this acyl chloride, no reaction is going to happen, right? This oxygen here, even though it has pairs of electrons, it will not attack the carbonyl carbon because this pair of electrons here is stabilized by resonance, like that, right? So what we have to do is we have to put some sort of base to it, like triethylamine T, or pyridine, right? So the most common one you'll see is like T, which looks like this, triethylamine, which is going to deprotonate the carboxylic acid, since this is a strong base, to give us this carboxylate here. Now, once you have this carboxylate, this negative charge here is more reactive, which is going to attack this carbonyl carbon, push the double bond onto the oxygen, and give us this tetrahedral intermediate right here. Right? Now, once we have this tetrahedral intermediate, chlorine is already a good leaving group. So we don't have to do any proton transfer steps here. Like we don't have to protonate this leaving group because it's already a good leaving group. So we could just reform the carbonyl and kick out the chlorine to give us our final answer, which is going to be this anhydride right here, which is the second most reactive derivative. Right. Okay. Now, let's make a carboxylic acid from the acyl chloride using neutral water. No heat needed, no acid or base needed, because this is the most reactive derivative. And this reaction specifically is hydrolysis, right? Because we're converting this carboxylic acid derivative back into the parent functional group, carboxylic acid, right here. Like that. Right? The mechanism is the same. Water, oxygen, attacks the carbonyl carbon, push the double bond to the oxygen, create this tetrahedral intermediate. We get this as a result. And then we could go back down, kick out the chlorine, get this final tetrahedral intermediate. And then you could use either a second equivalent of water or chlorine minus to deprotonate the positive charged oxygen to get you your neutral carboxylic acid right there. I used water here because there's excess amount of water compared to this one equivalent of chlorine right there, which is going to be the base to deprotonate this positive charged oxygen right there. All right. So the same mechanism is for when we make esters from acyl chloride. So let's have this acyl halide right there, and let's have this alcohol. To predict the product quickly, substitute the chlorine with the OR group of the alcohol, like that. Right? The mechanism is the same, but we now have an OR instead of an OH because we're using alcohol instead of water. Okay. Now for the amide right here, let's use this acyl chloride. We need at least 2 equivalent of amine for this reaction to happen, right? At least 2 equivalent of the amine or another base. And I'll show you why through the mechanism. So the nitrogen here with the pair of electrons is going to attack the carbon on carbon, push the bond into the oxygen, give us this tetrahedral intermediate. And now we're going to reform the carbonyl, kick out the chlorine, get this tetrahedral intermediate, where this chlorine here is a weak base. And because this is a weak base, this chlorine minus will not be able to deprotonate this nitrogen atom right here. So that's why we need at least 2 equivalent of this amine or another base. So the second equivalent of the amine is going to come by to neutralize and deprotonate that positive charged nitrogen to give you your neutral amide. Right? But if you were to predict the product quickly, you could just substitute this chlorine with the R and H and take away one H like that. Right? Okay. So the anhydride reactions are the exact same as the acyl chloride reactions, right? It's the exact same thing. But instead of the chloride here being the leaving group, the anhydride leaving group is going to be this carboxylate right here. Right? So it can do all of the reactions that the acyl anhydride can do. But it cannot create the acyl anhydride, acyl chloride, right? Like we can't do this in one step. Like if we have this anhydride right here, we cannot go to the acyl chloride in one step. But if this was a synthesis problem, what we can do is we could hydrolyze this anhydride using water, and we could use neutral conditions here. We don't need heat or a catalyst like an acid catalyst or base catalyst, because think of the acyl chloride and anhydride as the top 2 most reactive derivatives, right? And because they're the top 2 most reactive derivatives, we don't need heat. We don't need acid or base. This is just gonna hydrolyze this anhydride to the carboxylic acid right here. And we learned from like yesterday that we could convert the carboxylic acid to the acyl chloride using SlCO2 like that. And then once we get this most reactive derivative, acyl chloride, we could do many reactions. We could convert it to any of the less reactive derivatives in one step.
Wait, quick question,
Yeah.
sorry.
Mhm.
So I know we made the list and we had like increasing reactivity. So
Yeah.
if we had an alcohol or if we had like an amide or something else, and we hydrolyzed it back to carboxylic acid, would we need a reagent?
Yes. Like if we had ester or amide and we want to go back to carboxylic acid, we do need a base catalyst or a acid catalyst, right? If you're an acid catalyst, you need H2SO4 as the reagent. If you're in base catalyst, you need a negative charge version of the nucleophile, like a negative charge OH minus in basic conditions, like hydroxide
Okay.
ion, right? Um, Esters don't really need heat. Carboxylic acids don't really need heat unless you're trying to make the amide. If you're trying to make the amide, you do need heat because the amide is like the least reactive derivative. And then all amide reactions will require heat. Like if you're trying to create the carboxylic acid, I think that's the only thing I can do. Like create the carboxylic acid and Grignard reagents and reducing agents, that requires heat. Right. So let's go over that now. Like let's say we have this ester right here. We cannot create the anhydride in one step because the anhydride is more reactive than the ester, right? But let me show you why we can't do that as a conceptual thing. Let's say we have this carboxylate right here, right? And we try to have this carboxylate attack the ester, carbonyl, push the double bond onto the oxygen, create this tetrahedral intermediate, right? Now, once we get this tetrahedral intermediate right here, if you want to get to the anhydride, you're going to want to reform the carbonyl and kick out this OR group, right? To get to the anhydride. But this would not happen because this is not the better leaving group. The better leaving group is this right here, which is why when we go back down to reform the carbonyl, we're going to kick out this group to go backward to what we started with. So you could think of this as no reaction, essentially. Right, so that's why we cannot create the more reactive derivative from a lower reactive derivative. Right. So let's just say this is no reaction. Right. Or like if it does happen, the equilibrium arrow would go more towards the left. Right, because that's what he put in his lecture slides. Like it's gonna go like that. Oh no, the other way. This, that, this, that. Right. It does not want to go here. Right, because this is a terrible leaving group. Bad leaving group. If it leaves, it will leave like this, where the negative charge here is less stable than the negative charge here, right? Because this negative charge can do resonance with the carbonyl. And because this is the better leaving group, if we reform the carbonyl, it's going to want to kick out this group here instead to go backward there. Right. Now, this would require like, actually, no. Estates don't need that. Okay. So now let's say we have ester and we try to create the carboxylic acid through hydrolysis with neutral water. This right here will be no reaction as shown because this ester here is the lower reactive derivative. It's not the top two most reactive derivative. It's not an acyl halide. It's not an anhydride, right? So we have to put an acid catalyst like H2SO4 to activate the electrophile, right? Like we went over this like 2 nights ago. This is the addition elimination mechanism in acidic conditions. So just for review, the first step here is to protonate the carbonyl oxygen with the strong acid that we have, H2SO4. When we do that, the carbonyl carbon right here becomes activated. It becomes a bigger partial positive charge. It becomes more electrophilic, right? Which allows the weak nucleophile water to then attack the carbonyl carbon and push the double bond onto the oxygen, right? Before, if the acid was not there, this water right here that was neutral, the oxygen is not able to attack that weak electrophile, carbonyl carbon. It is partial positive charge, but it's a small partial positive charge. The point of the first step here with the acid is to make that positive charge bigger, make the carbonyl carbon a better electrophile, right? Which allows this weak nucleophile to attack, push the double bonds to the oxygen, and give us this tetrahedral intermediate right here. Okay, now we could do this next proton transfer step in one step. We see that this group right here is the new group that we just added. This group right here is the old group that we have. We want to eventually get rid of this old group and we want to eventually keep this new group. We want to keep this group. We want to kick out this group. But right now, as shown, this right here is a good leaving group. This right here is a bad leaving group. That's not good right now because like we want to reverse them. We want to keep this group right here. We want to kick out this group right here. So we could convert the leaving group ability by doing that, right? We could protonate this group and deprotonate this group at the same time, right? You're gonna deprotonate the group you want to keep to make it neutral, bad leaving group. And then you're going to protonate the group you want to kick out, make it into a good leaving group, which is going to give us this tetrahedral intermediate right here. Okay. Now, once we have the bad leaving group in place and the good leaving group in place, we can reform the carbonyl and kick out that good leaving group that we just formed right there. And that's going to give me that last intermediate, where the last step here, we could deprotonate and neutralize the positive charged oxygen with the conjugate base HSO4 minus, which is going to give us that carboxylic acid right here. And because we went back to the parent functional group, this was hydrolysis, right? We came from a carboxylic acid derivative back to the parent functional group. That's hydrolysis. And hydrolysis will most likely have water with it. Okay. We could do the same in basic conditions, right? Basic conditions is way quicker. Like, instead of neutral water, we can have OH minus, like NaOH or KOH. But water is most likely going to be the solvent. That's going to be the proton source. OH minus here is going to attack the carbon-to-carbon, push the double bonds to the oxygen, create an OH right there, OR right here. And now this is the weird step here, right? In basic conditions, this is now considered able to leave in basic conditions, right? Before, in acidic conditions, that is not able to leave. But because we're in basic conditions, we could reform the carbonyl and kick that group out to give us our final answer. When we're gonna get this carboxylic acid right here, right? But because we're still in basic conditions, this carboxylic acid will get deprotonated to get to the carboxylate, right? And then assume acid workup like H3O plus second step, you're gonna get back to the neutral carboxylic acid. But this process right here, when you get to this carboxylate from an ester, that process is called saponification, which makes soap. Like, this is how they make soap, right? Saponification is basically another way of saying hydrolysis of ester in basic conditions. Hydrolysis of esters in basic conditions. And you do need to know that name because he does include it in his multiple choice sometimes or explanation problem sometime on an exam. Saponification. Ester to carboxylic acid or carboxylate by hydrolysis. Okay. Yeah. Now we could go on to the ester to amide. And in this one, we don't need any acid or base catalyst, but we do need heat here. If you're trying to create an amide from an ester, you do not need acid or base catalyst, but you do need heat, right? And the mechanism is like this, where it has both acidic and basic components of the mechanism here. Right? We could, yeah, I think he accepts both ways. Go back down there. Well, actually, no, let's, yeah. We don't want to do that because last night we said that this oxygen here, right? Even though we want to make this into a good leaving group and we want to make this into a bad leaving group, this oxygen here is not able to grab the hydrogen of the nitrogen and deprotonate this nitrogen group and protonate this oxygen group because nitrogen is more basic than the oxygen. It wants to keep this hydrogen more than the oxygen does, right? So this is the tricky mechanism here where we're just gonna kick out that OR minus group, which is gonna come back and deprotonate the positive charged nitrogen at the last step to create the neutral amide right there, right? Which is included in the mechanism of the no-core diacetyl for mention 1, right there. If you're going from an ester to an amide, but the same thing for predicted product still applies, right? Like, you just substitute this OR group with whatever the nucleophile is, -1 hydrogen. Okay. Now for the amide, it doesn't really do much because it's the least reactive derivative. like other than nitrile, what it could do is it could do hydrolysis in acidic conditions with acid, water, and heat, and that's gonna get back to the carboxylic acid. The mechanism is the same in acidic conditions, right? Like we did earlier. Now, if you have a nitrile like CN, like this, which is also represented like this, there's a triple bond between the carbon and nitrogen right there. If you do hydrolysis of a nitrile, it will also go to a carboxylic acid, right? You do need heat here as well. But the intermediate of the mechanism is gonna be an amide. And from that amide, because we're still in acidic conditions with heat, that's gonna hydrolyze into the carboxylic acid. And the reason why I drew it like this is because there's 3 carbons of this nitrile. 1, 2, 3. 1, 2, 3, which is this 1, 2, 3 carbon right there. And this amide here is going to then give us this carboxylic acid right there through hydrolysis, like that. Right. Any questions on those reactions that we went over so far? Like, we went over the interconversion between the derivatives.
No.
That's good. That's good. There are organometallic reactions, right? Actually, let me just copy and paste that right here. Yeah, this the big reactions for midterm 1. Okay, so this is the interconversion between the carboxylic acid derivatives. Acyl chloride and hydride, those are the big 2, right? Those big 2 do not require heat, do not require acid or base. But everything else right here requires acid or base. Except when you're trying to make an amide. If you're trying to make an amide, then that is going to require heat for carboxylic acid. Ester, right? I put the special side notes in each product to show you the differences between the reactions. And the green here is assuming acid workup because this is in basic conditions with the hydroxide ion. So the final answer should have that carboxylate actually in basic conditions because we're going to deprotonate that carboxylic acid, right? But assume acid workup, which Helix does. You could put this as the final answer and you still get full credit for that. Okay. Now using this chart, I'm gonna give you guys practice problems and then move on to 118B and then go back and do the organometallic and hydride reagent reactions. Right. Okay. So let me give you guys practice problems here. Oh, there's also intramolecular ones as well, which is like a different set of reactions. It's the same mechanism, but it's a little bit more wonky because you're gonna break a ring or open the ring. So I'm gonna include that in this practice as well. Try that out. I didn't go over it yet, but it's the same mechanism. Just a little bit weird because you're gonna form a ring or break a ring. Okay.
Ryan, I don't remember 118B.
118B? Okay. I'll leave that at the end then, and then I'll come back to it
Okay.
and then do it if you can't figure it out. But I'll give you warm
Perfect.
up ones to build up to that.
Okay.
Uh-huh.
What is it, like William Ethers or something?
Wilson ether synthesis, that's 118A, but that does have an
Oh.
intramolecular part of it as well. Like you're thinking of the intramolecular Wilson ether synthesis, which creates the epoxide in 118A. Let's see. Now, this last one here is the intermolecular one. Okay, 1, 2, 3, 4, 5, 6, 7. Yeah. The 6 problems here are intermolecular, right? And then the last one here, the 7th one, is intramolecular. Okay. 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 Let's move on to 119B. Kelly, did you have any questions or topics you wanted to go over for 119B, or move on to the next set of reactions for the alkene? Let's see. Let me show you the next set of reactions. Yeah, I want to show you the electrophilic addition reaction. So let's say, do you remember carbocation stability from 118A? Like what makes a carbocation more stable than the other? Yeah, tertiary is the most stable, then secondary, then primary, then methyl is the least stable, right? That's because of something called hyperconjugation, right? The more substituted the carbocation is, the more stable it's going to be, right? They could think of it as more friends, more stable around the carbocation. Okay, so keep that in mind, because that's going to be a big part of this next set of reactions. When you have an alkene, think of the alkene as a nucleophile and base. So this alkene here is a nucleophile and base, specifically the carbons of the alkene. So the carbon right here and the carbon right there. Let's say I introduce it to a strong nucleophilic acid, HX, where X can be chlorine or bromine. Let's use bromine. So let's use HBr. So if I have this alkene reacting with HBr here, this is a strong acid, this alkene is a base. So we're going to do an acid-base reaction here. We have to choose which carbon is going to act as the base. It could either be this carbon, or it could be either this carbon right here. To choose which carbon is going to be the base, we're going to choose which carbon is going to be the more stable carbocation. So I'm going to label this carbon A and label this carbon B. Which carbon would be the more stable carbocation? Carbon A or carbon B? Yeah, carbon A, right? Because carbon A is more substituted than carbon B. That's why we want the carbocation, right? That means carbon B is the one that's gonna be the base and grab the hydrogen of HBr, take out the Br, right? The reason why the less subcarbon grabs the hydrogen is because, I'm gonna draw that out right there. If I highlight this hydrogen here in yellow, that's this yellow highlighted hydrogen right there. Does this carbon grab that hydrogen, right? Which you could imagine this double bond right there is that bond right there, right? This carbon here used that purple bond to grab that hydrogen, which makes this carbon here, carbon A that we said, lose a bond, right? Because it lost the bond, we now have a positive charge right there, right? So that's why the less subcarbon grabs the hydrogen from the acid, And once we have that carbocation intermediate, the Br minus is going to then be the nucleophile to attack that carbocation electrophile and give us our final answer here. Now, because, well, do you remember the hybridization of this carbocation? Like, is it sp, sp2, sp3? And what does it say about the geometry of that carbon based on the hybridization? sp2, yes. And sp2 carbons are trigonal planar, right? Making them flat and planar. So when the Br minus comes in to attack, it can attack on the top side, giving you a wedge product, or the back side, giving you a dash product. But in this case, it doesn't really matter because we don't have a chiral center here, right? This is not a chiral center because we have two methyl groups. But let's say this was a chiral center, you would have enantiomers, right? You would have one product where the bromine is a wedge, and you have one product where the bromine is a dash, giving you enantiomers right there. If that was a chiral center, right? So keep that in mind for stereochemical questions, right? Like, is this because you're gonna see these some reactions are syn addition, anti-addition, none. This reaction here is none, right? The reason why it's none is because when this carbon here of the alkene grabbed the hydrogen, it grabbed it like randomly, right? Because this was a flat carbon. It could have been top or bottom, and this Br minus here, when it comes into attack, it attacked it randomly. It could have been top or bottom as well. So you don't have to worry about the stereochemistry here. It's random. It's randomized because of that flat sp2 hybridization that you talked about. Any questions on that? This mechanism, so far? Is the chiral center only determined by the carbons attached to the carbon we're looking at? The chiral center means that carbon has 4 different groups attached to it. 4 unique groups attached to it. This carbon right here has 2 methyl groups, so we cannot consider that a chiral center. But if that was an ethyl group, then this carbon here would be considered the chiral center, right? Which would come from the carbocation. You can have another chiral center in the molecule floating around like this, right? But this chiral center here will be untouched in the reaction, right? Because the alkene is not touching that carbon at all. Nothing touches that carbon right there. And if nothing touches that carbon and you form like one wedge bromine here and another product where the bromine is a dash, do you remember what would be the stereochemical relationship between these two molecules where some chiral centers change, some chiral centers change, right? Enantiomers is when everything changes, but there is another stereochemical relationship when some change and some stay the same. Diastereomers, yes. So if you have another chiral center present and nothing touches that chiral center, that stays the same, but you do change like one of the chiral centers, then these would be diastereomers of each other, and you would have to draw out both of these products in the product. Right. So watch out for that as well. So the one I just had 2 answers, yes. And I'm gonna draw that out for you more specifically to make it more clear. So let's say we have this alkene right here, and we have this group. Oh shoot, no, I don't want to do that because that's gonna go into something else. I'm gonna show you that after. I'm gonna make it this far away to avoid that thing. Let's do HCl. What do you think is gonna be happening in the phase step of the mechanism here with this alkene and HCl right here? The Cl attaches to one of the carbons on the alkene and the double bond goes away. Yes, the double bond will go away. The Cl will attach to one of the carbons of the carbon. Which carbon though? The more subcarbon or the less subcarbon? And this is going to go to a different term. Right? Markovnikov or anti-Markovnikov? More sub, yes. And that more sub carbon is referred to as the Markovnikov position. Right, so it's just a fancy name of saying more subcarbon. More subcarbon, Markovnikov. less subcarbon, and Tarmakov-Nakov. Okay, so that's how you predict the product quickly. But to show you the mechanism, here's what the mechanism would be like. We want the carbocation to be at the more sub position because it's more stable at the more sub position. So that means the less sub carbon is going to attack the hydrogen of the HCl, kick out that Cl, form this carbocation intermediate right here. And now there's a reason why I drew this carbon center far away. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. Because I'll show you why I did that when I go into the next thing here. Now, once of this carbocation, the Cl minus is going to then attack the carbocation. But because this carbocation here is sp2 hybridized, flat and planar, the Cl minus could have attacked at the top side, giving us a wedge Cl. Or it could have attacked on the bottom side, giving us a dash Cl. Right? The other carbon center here with the isopropyl and wedge stays the exact same. Nothing touched that carbon. Right? And this would be our two answers here, two products there for this reaction. 50-50. Oh, well, I wouldn't say 50-50, but these would be diastereomers right here of each other. Right? Like you get like mixed yield of these two products here, which will be like equally major, right? Like equally major. So you would have to include both of them as an answer. These are not racemic mixtures, right? That's a good point. Racemic mixtures refers to a 1-to-1 ratio of enantiomers, and that's the most important thing, right? Enantiomers. Because these are not enantiomers, we cannot call them racemic mixtures. These right here are diastereomers, not enantiomers. So we can't call them racemic mixtures. Racemic mixture, right? A racemic mixture is when we have a 1-to-1 ratio of enantiomer, right? Yeah. Did Cagley trick you guys with this as well, or probably? But she should probably get into it this quarter. The 119B, like how these are not racemic mixtures. Next week. Okay. Now, yeah, racemic mixture stuff last quarter. Yeah, like enantiomer, diastereomer, racemic mixture, meso, molecule, RS, plane asymmetry. Yeah, I know. Like that goes more in depth. Like 118A stuff like goes like way more in depth with the foundational stuff like resonance, stereochemistry, nomenclature for sure. Well, nomenclature sticks throughout the OChem series. Like when you learn neofunctional groups, you're gonna learn nomenclature like every time. Spectroscopy is always gonna be there. Acid-based stuff, especially for 118A. Right, so let's try this one here. And let's react this with HBr. Describe to me the mechanism. Like what's gonna happen in the first step of the mechanism. And I'm gonna draw out the HBr like this, where there's the bond drawn out explicitly between the H and Br. This H here is the strong acid. Which carbon do you think wants to grab that hydrogen, A or B? So if B grabs the hydrogen and kicks out the Br, we're gonna have this carbocation right here, right? Because B carbon would have the hydrogen, it will maintain neutral. Yes, I think you were thinking about the carbocation, right? Where the carbocation would be more stable at. Yeah, we want the carbocation at B, but because we want the carbocation at B, the other carbon grabs the hydrogen and kicks out the bromine to form the carbocation at the more sub position right there. Okay, now once we have this right here, what's the next step? This one here, I did not go over yet. So be careful. This may be a tricky one. What's the next step after we form this carbocation intermediate? Not a methyl shift, but a hydride shift, right? We will do a methyl shift if there's no hydrogen present. Because there is an invisible hydrogen present here, we're gonna do a hydride shift, right? So you have the right idea in mind. We're gonna do a carbocation rearrangement, but it's not a methyl shift, right? We will do a methyl shift if there's no hydrogen present. So when we do that hydride shift right there, we get the carbocation at the more sub position right here, where the methyl here that was a wedge becomes flat and planar, because this carbon is not sp2 hybridized, right? Where the last step here is to have the Br minus attack the carbocation right there and give us our final answer. And I'm going to draw this out to show you the two different products here. That's one of the products. And this is the other product right here. And would you say these are enantiomers of each other? Or diastereomers of each other? Would they be enantiomers or diastereomers of each other? Those two molecules. Enantiomers, yes. Because there's only one chiral center of this molecule, and that one chiral center changes between the two molecules. Enantiomers of each other, and it's a 1-to-1 ratio of those enantiomers. And this right here is a racemic mixture. And that's the more common one you'll see in practice and then the problems you see. The previous problem did not do a hydro shift. That's a good question, because this is too far away to do a hydro shift, right? Initially, when I gave you this problem right here, I drew out the isopropyl right here. But then I was like, let me draw this chiral center far, far away, so I don't do that hydride shift or methyl shift. Right, so that's why it doesn't do it, because this is way too far away from the carbocation. Yeah, there's still an H in here, but because it's so far away, the hydride shift is going to be in low yield. Oh, this carbon right here, we don't do a hydride shift here because this is a secondary position. This is also a secondary position. So it's already at its most stable position. Yeah, it could be at. Right, and we don't want to do extra work to move that carbocation. It's going to stay as it is, where it's at right now. Okay. Now let me give you a practice problem here to try out. Let's see. I want you to draw out the mechanism and the product as well, because this is a testable mechanism here. And I want you to tell me if you would form enantiomers as the product or diastereomers as the product. Okay, try this problem out here. Okay, Suparna, Alicia, were you guys able to complete these problems here? Wait, I think you guys have lectures Monday, Wednesday, Friday, right? Like Helix and Kagli. Is there a section where there's Tuesday, Thursday section for Helix or Kagli? Or is it like only Monday, Wednesday, Friday
I
section?
think there's two sections. I think there's a Tuesday, Thursday, but I think it's 2 hours, and then there's a Monday,
Uh-huh.
Wednesday, Friday, which is like 15 minutes.
20 minutes? Yeah, I see, I see. And you're in the 15-minute one, the Monday, Wednesday, Friday one?
Yeah.
I see. Yeah. Cagli's the only one teaching one to be one section. I see. Monday, Wednesday, Friday. Okay. Yeah. So the predicted product for the first six, I would say, or actually the first five, I would say, is like substitution, basically. You just quickly substitute the leaving group of the derivative with whatever the nucleophile is. The fifth and sixth one is a little bit tricky. Right. Were you guys able to predict the product, or were you guys doing the mechanism for all of these?
I did the mechanism only because it helps
Uh-huh.
me predict the
Yeah,
product
that's
because
good.
like I like explain it to myself.
Yeah, yeah. That's the better way to do
But
it. Like that, that's how
I
I
got
actually
stuck
prefer to do
on the
it.
last one.
The intramolecular one?
Yeah.
Okay, before we get to that, let me check your other ones first.
Like you said, it's basic substitution.
Uh-huh.
Wait, I
Yes.
had a quick question on
Uh-huh.
the first one. For the examples that you did, you had like TEA or a strong base. Did we not need one?
T.
Yeah, T.
So that's the one with the amine, right? So if you have
Oh, I
two
see.
equivalent of the amine, you don't need T. But if you only have one equivalent of the amine, um, like let's say one EQ, you do need T. Or pyridine, PYR, which is uh the structure here. Right? So that's the one with the amine. But if you have two equivalent of the amine, then you don't need a base. If
Got it.
you're
Okay.
given two equivalent of that. Yeah. So I'm gonna draw out the products here and let's see if you were able to get them. Wait, did I draw H2SO4 here? Was that
I just
H2SO4 there?
assumed you did.
Okay,
Like, I just
okay.
assumed that you just forgot it.
Yeah, yeah, yeah. It's supposed to be there. If that's not there, you would put no reaction, and that's a Leavens thing right there. Right, so that's good. That's good. That's good that you assumed it. Know that that requires acid, but it could not happen in basic conditions because in basic conditions we're gonna deprotonate the acid. Okay, that's gonna be like that. Like that. And this one here is gonna be oh this. The carbon center stays the same. Nothing touched that carbon.
Oh shit. Okay.
Uh-huh. Did you forget the
I changed the
stereochemistry?
chirality of it
Oh,
because I
you made it
thought,
into a dash? That's worse. Oh my
yeah.
gosh.
I literally forgot chirality.
118A, yeah. Yeah, because like in the mechanism, like if you drew it out, you see that nothing touches that carbon, right? Nothing reacts with that carbon. So the chirality of this carbon stays the same.
Okay, got it.
Uh-huh. Okay. Um, were you able to get the last one here?
No. Can you
Uh-huh.
draw the mech for it?
Oh, wait, I mean, I meant the second to last one, the one with the nitrile.
Oh, wait, I didn't, for some reason, I don't think I copied that down.
Oh, uh-huh. I see. So this CN here is a nitrile. The tricky thing about this is that we know this is hydrolysis because we're putting it through acid, water, and heat. We're gonna convert it back to the carboxylic acid, but the C of the nitrile is the C of the carbonyl carbon of the carboxylic acid, right? So if I color code it in blue like that, that's this blue carbon right there, right? A lot of people would have drawn this as the product right here, right? But this is wrong because it's missing a carbon, right? This is not correct. Missing carbon. Okay. Okay, now let me draw the mechanism for the last one, the intramolecular one. Okay. Well, actually, I'm gonna walk you through it. what do you think is gonna happen in the very first step with the strong acid? Like, what is the strong acid gonna protonate? Like, we have 3 oxygens here that we could choose from.
The third one, like the uh carboxylic acid thing, like
This one, right?
yeah.
So when you see a carboxylic acid
Oh, is
derivative right
that
here,
resonance?
yeah, it's resonance stabilized. So we would not protonate that oxygen right there. We're gonna protonate the carbonyl oxygen, right? And that's
Is
another
that not
important
also
thing.
resonance stabilized?
This one here, we can't go down to make a triple bond
Oh,
there.
I see. Okay.
Yeah, we can't do that. We can't do that. Uh-huh. Another way to look at it is like this. Like, let me put that carboxylic acid right here. If you protonate this oxygen here of the carboxylic acid, you're gonna get this as the conjugate acid, and then we see that that oxygen can make a double bond right there. Whoa, whoa, whoa.
Wait.
Whoa. Wait, hold on. What is this gonna make? This is gonna make a very bad resin structure. So this is even worse. 1, 2, 3, 4. This is positive 2. So that's worse. But that is able to do resonance. Well, no, that's not able to do resonance. Not able to do resonance. This is bad. This is bad. But if we were to protonate the carbonyl oxygen right here, right? This right here is a better resonance structure, right? We can actually do that. Push the one to the oxygen, create the more stable resonance structure right here, right? So this guy is way more happy than this guy. This guy is very bad, very angry. So because we are not really gonna do this resonance structure, this is unstable, which is why this would not likely get protonated. But this carbonyl oxygen here is likely to get protonated because that leads to the more stable conjugate acid that is able to do resonance well. Right. Any questions on that concept?
Wait, so it can do resonance or it can't do resonance?
This one here cannot do resonance.
Okay.
Cannot do resonance. Right? And because it cannot do resonance, we cannot protonate this oxygen right here because that would lead to an unstable intermediate, unstable conjugate acid. But we can protonate the carbonyl oxygen because that would lead to a more stable intermediate, more stable conjugate acid that is able to do resonance. Right? And because the intermediate is more stable, the carbonyl oxygen is more basic. Right? And that's for any carboxylic acid derivative, like acyl anhydride, ester carboxylic acid amide. When you put it through strong acid H2SO4, the thing that gets protonated first is the carbonyl oxygen. Right? The carbonyl oxygen because that leads to a more stable conjugate acid. Right? So this carbonyl oxygen here is the base that would get protonated. Base that gets protonated. Protonated by H2SO4. Okay. Okay. So we're gonna protonate the carbonyl oxygen, kick out the HSO4 minus conjugate base, give us this intermediate right here. And what's the effect of the carbonyl oxygen? Like as a result, like after we protonate the carbonyl oxygen, what happens to the carbonyl carbon's electrophilicity? Does it become bigger or smaller?
Wouldn't it become smaller?
Um, it would become bigger, right? Think of it as
Isn't
like
it because it's not as electronegative as just a plain OH, like just a plain negative oxygen atom?
uh like if this was a neutral carbon and oxygen atom right here, this carbon to carbon is a partial positive charge, but not as big, right? So it's a weak nucleophile right now. But when we protonate it, think of this positive charge oxygen as very angry because it does not want that positive charge, right? And because it's very angry, it's gonna want to withdraw even more. It's gonna like want to pull on the electrons even more on this carbon.
Wait, does the alcohol not like take some of that charge away from it though?
The alcohol will have the same effect as the one previously right here, right? So the alcohol here will don't be able to donate electrons into the carbonyl, but it does the same exact same thing for this one right here as well, right? So the alcohol does donate electrons, but the effect here there we could ignore because it does the exact same thing for two of these molecules, the neutral one and the positive charge one, right? But this positive charge one here makes this more unstable, right? And if it's more unstable, think of it as more reactive,
Oh, okay.
right?
So remember you talked about like sharing charge with things and it made the electronegativity of a carbon smaller.
Oh, that was when I was comparing the derivatives. Like
Oh, okay.
when I was comparing acyl chloride with, let's say, ester. Like this oxygen here is less electronegative than chlorine, so it's more willing to donate electrons to the carbonyl, making the positive charge of the carbon smaller. But this chlorine here is more electronegative, so it's not as willing to donate electrons to the carbonyl.
Right. So it wouldn't work like the electronegativity of that carbon wouldn't be smaller, like with the same logic. Oh, it's only if it's a neutral O.
Like this neutral O, like we're comparing it between this and this right here.
Oh, okay,
Right,
I
right.
see. Okay.
But if we were to compare this oxygen here that is positively charged like this O here would be bigger. Like this
I
positive charge
see.
of this carbon here would be bigger than this positive charge carbon right there.
Okay, just because it's more unstable. Okay,
Yep,
got it.
because this is more unstable, yes, and more reactive. Right. Right. Mm-hmm.
Sorry.
That's okay, it's okay. It's a lot, it's a lot. Right. Okay. So now like that's why this positive charge here is bigger than this positive charge because it's more unstable. Right. But we can ignore this factor because they're the same atom, oxygen and oxygen right there. Right. Now, usually when we have this activated electrophile, we have some sort of nucleophile that's neutral to attack that carbon right there. But we don't have anything on the arrow, but we do have something here on the molecule, which is that alcohol. So we're gonna do an intermolecular reaction where the nucleophile is on the same molecule as the electrophile, which would create a 1, 2, 3, 4, 5-membered ring, which is gonna be this 5-membered ring right here, which is 1, 2, 3, 4, 5. Right? Where 2 has this R group, 3 has that methyl group, 5 has this OH group, and atom 1, oxygen, still has that hydrogen right there with the positive charge. Now this is where we do the proton transfer step, where we deprotonate the group we want to keep, protonate the group that we want to kick out at the same time, right, to save time, to get us to our desired tetrahedral intermediate. And then once we have that, we can reform the carbonyl, kick out the leaving group that we just formed, give us our last tetrahedral intermediate. Oh no, last intermediate here. And the last step is to deprotonate and neutralize the positive charged oxygen with the HSO4 minus to give us our neutral product, the cyclic ester. Right? And the cyclic ester has a name, a general name. It is the lactone. Lactone is a cyclic ester. If you create a lactam, that's a cyclic amide. If you create an imide, that's a cyclic amide anhydride. I don't know. A cyclic something like this. Like that. It's like an anhydride looking structure, but instead of oxygen, you have nitrogen right there. Right, but because we created a cyclic ester, the carbonyl with the OR group, this is a lactone. And this is a result of an intramolecular reaction. All intramolecular reactions would form a ring. And this is the ring right here. Right. And this is basically intramolecular Fischer esterification, right? Because we see our starting material was a carboxylic acid, and we reacted it with acid and alcohol, which leads to an ester. So that's intramolecular Fischer esterification, because we created an ester from a carboxylic acid with alcohol and acid. Okay. Any questions on that one?
No.
Let's get. Okay. Kelly, were you able to do this one? Let me see. Yeah, protonate, carbocation right there, hydride shift, chlorine minus attacks. Yes, you got the right answer, right? But what would the stereochemistry of that chlorine be like? Would it be wedge? Would it be dash? Or could it be both? Yeah, it could be both. And if it could be both, would these be enantiomers of each other or diastamers of each other? The two products that we're gonna have. Like that. Diastamers, yes. Because some chiral centers change, right? Which is the green one right here. That chiral center in green changes, but the chiral center in pink stays the same. So these are diastamers of each other. You cannot say that this is a racemic mixture because they're not enantiomers of each other, right? So that is a stereochemical thing right there. Nice.